Daylight savings, huh? Brutal. Although I talked to someone this morning and he's like, not really, I just went to bed at the same time. I was like, that's fair, but still felt a little bit tough today. Okay, so you got your practice test too. I know I'm springing this on you. Remember, it's just for completion marks, so give it a fair shake, and then we'll go through it together on Wednesday. Okay, so just show me that you tried a bit of it. Let's say 2 or 3 questions at least, and then you'll be good to go, okay? But then, of course, you'll want to do the practice test for the actual test anyways, but we'll go through it together on Wednesday. But for a completion mark, which is a nice booster for your assignment grades, right? You can do some of that practice test. Okay. Notice that there's 5 questions on the practice test, right? And so the first one will definitely be on there. There'll be that kind of question on there. Okay. And then for the second, third, fourth, and fifth question, there's going to be all of them, but you choose. So you read them and you decide which ones you're going to do, and then you can leave, I'm going to say 2 of them. Okay. So there's 1, 2, 3, 4. You have to pick 2 out of the 4, do those, and then tell me the type that the other 2 are that you're not doing. Okay. So it won't be this long at all, right? But I have to give you, or I want to give you practice for all of it, right? So question 1 for sure, and then let's add a little note here. So March 11th, crazy. Test number 2 on Monday. I have that right? It's on Monday. You guys have it written down somewhere? I do, but yeah, Monday. On Monday, March 18th. Is that Monday? Great. March 18th. And so see practice test number 2. Question 1 for sure. And then question 2 through question 5, I think, right? Yeah. Question 5. Pick 2. Okay. And tell me the type, right? So you have to tell me the type of question each of them are. And tell me the type of question for the other 2. Okay. Hopefully that makes sense, right? So you'll have lots of questions, and then once you're doing assignment 5 and you're doing the practice test, you'll have a pretty good idea of the types of questions that you like to do. You're always going to be doing a hypothesis test followed by a confidence interval. So there's no question there. It's going to be a hypothesis test and then make a confidence interval, right? So that's going to be the same for all of them, right? But do you like one sample means sigma known, or maybe you like matched pairs, or maybe today you'll see 2 independent samples, right? Maybe you prefer to work with those, mostly because they're the easiest to identify, right? What type of question is it? If it's easy to identify, then you know you're on the right track, right? And so, so that's going to be the layout for test 2. So do at least 2 of the practice problems on the practice test and show me your work on Wednesday, March 13th, for 1 completion mark. Same as last time. So if you do like a compare and contrast with assignment 5 and the practice test, you'll see that all of these look very similar, right? Here's a problem, do a hypothesis test, do a confidence interval, that type of thing. Test 2 is essentially just assignment 4 and assignment 5, just from there, right? So, any questions before we get started? Yeah. So, if you didn't get assignment 5 last day, they're up here, or even the chapter 5 notes, I think everyone has, but I have some copies here, and the practice test for next day. All right. So where were we? So last day, we kind of ended on Jocko's garage. We were going through this hypothesis testing question for matched pairs. And we said, okay, well, if we have matched pairs, or when we have matched pairs, we have 2 observations on the same individual or on the same subject, right? And so here we have the same car, right, with some amount of damage, right? Some cars don't have that much damage if they're going to get fixed, and some cars have a lot of damage, and that's going to affect the estimate that you're getting, right? And so the insurance adjusters are concerned about the high estimates they're getting from Jocko's garage. So they took the estimates, so they have a car with, doesn't look like that much damage, right? 500 is the estimate from Jocko and 430 is the estimate from the trusted garage. And then to compare these, right? Because taking the average of this group and the average of this group, these high estimates are going to get mixed in with these low estimates, and you're not going to be able to pull any information out of that, right? And so what we do is we calculate the differences, right? So for matched pairs, we're analyzing the differences, and then we can calculate the mean and the standard deviation of the differences, and just ignore all this because everything that we need is just here in the 1 column of differences. So now you've reduced this to just 1 sample, right, with sigma unknown because you've calculated the standard deviation from your sample, right? And so now you're just back to the first case, 1 sample mean, sigma unknown, and you just apply the same techniques, right? And so we went through and we talked about, okay, so calculate the differences, and then we pretended to find the mean and the standard deviation. I just gave them to you after, but it might be good, or I don't know, not pertinent, but good to practice calculating the standard deviation. I don't think I saw one on the final, but if there is, I'll warn you, right? But it'd be good to do some math. I don't know. So we're on C, set up the null and alternative hypothesis. We talked about, okay, well, if we have matched pairs, right, and we're analyzing these differences, it's hard to know which way the sign should go, right? Because if we have a one-sided test for matched pairs, then we need to figure out, okay, well, what does that mean in terms of the differences? So if we want to show that Jocko's estimates are higher than the trusted garage, right, then we have to look at how did we calculate the differences, right? Because that's going to change which way the sign is going, right? And so as long as we're consistent where how we calculated our differences, right? As long as we calculated the difference as Jocko's minus the trusted garage, then if Jocko's estimates are higher than the trusted garage, right, consistently higher, then the difference must be positive. Another way that you could kind of cheat that is, or what I kind of do is, I look here and I say, well, this estimate is an estimate where Jocko's estimate is higher than the trusted garage, right? And when I calculate the difference is positive, right? And so then I know if Jocko's estimates are always higher, then the difference, or the mean of the differences, mu subscript d, must be greater than 0, right? Because I want to show that Jocko's estimates are higher. For this reason, for matched pairs, it's a lot easier if you have a two-sided test, right? You just want to know if there's a difference between these two estimates, right? But here we're specifying, no, our Jocko's estimate's higher than the trusted garage. Okay, so it requires a little bit of extra thinking, but then once you have your null and alternative hypotheses set out, then it's smooth sailing, right? And so we can move on to D, where we have to find the test statistic. Hard to say, easy to do. So let's see here. I'm actually gonna pull the numbers from here. Sure. D, find the test statistic. Basically, I'm just walking you through the steps of the hypothesis test, right? Because the test statistic here is T is X bar of the differences, or subscript D if you want. I think we had just D in our notes. But on the formula sheet, I still have the diff, doesn't matter, minus mu subscript D, technically, divided by S subscript D over the square root of N subscript D. What we said here, oops, for matched pairs, recall, H naught is always that mu D equals 0. So there's nothing that you need to change in the null hypothesis for matched pairs problems, right? And that's what's going to be nice about matched pairs, but also two sample means that you want to compare is that the null hypothesis is going to be fixed, right? So there's nothing that you need to pull from the question and figure out there. So that's what's nice about those problems. I'm just thinking ahead to test 2 where you have to pick ones that you like, right? A lot of it hinges on having the right null hypothesis and alternative hypothesis. So it's good to have those laid out. And so mu D is 0. X bar of the differences, so the mean of the differences was 80. And the standard deviation of the differences, should have shortened a little bit, but whatever, 84.59052 divided by the number of the differences is the number of cars that we have, right? There's only 10 differences, and so we have a sample size of 10. So now, oops, we have 84.59052 divided by the square root of 10. I don't really trust this calculator, so I get 80 divided by 26.74987117. Hopefully you're getting the same thing. 80 divided by that, 2.990668609. T always gets rounded to 3 decimal places, right? Just to match the table. And so we have to round this to 2.991 to 3 decimal places. Add another page here. Oh, what happened there? So already with this high of a test statistic, right, or this high of a t or even a z, they work the same way. We already suspect we're going to reject the null hypothesis, right? So, but we have to find the p-value to make sure that that's the case. So step E is find the p-value. Find the p-value. So this is when we use the t-table, and we just outline exactly what we're doing, right? When we go to the t-table, we think, oh, okay, we need to find our degrees of freedom. So I just write all that out, right, to communicate to, well, I guess myself, because I'm marking it, that I know what I'm doing, right? It's your job to explain everything that you're doing so that I can just say, oh, okay, they know what they're doing, right? So using the t-table, with degrees of freedom equal to nd minus 1, which is 10 minus 1, which is 9, we find, so even before going to the t-table, we can set up this blurb. And also, what I do is I put my calculated t and absolute value brackets in the center of the page, right? Because then I'm going to put the values that flank it on the other sides, or on the outsides. So I have something like this. So absolute value of t equal to 2.991 is caught between 2 values. I can even keep going, bless you, and fill in kind of this empty shell, right? Because now the next step I know is that I'm going to find the p-value, and I'm going to be looking for the one-sided p-value, right? Because I'm only concerned with Jocko's estimates being higher than the trusted estimates, right? And so the one-sided p-value is going to be between 2 values. Okay. So before you even go to use the t-table, you can set up this kind of empty shell and then just fill in the values once you're in the t-table. Okay. So if we go to our t-table, we only have 9 degrees of freedom. And so we're here on the 9 degrees of freedom line, and we're taking our 2.991 and we're just moving out into the tail to figure out where we would fall. So we would fall somewhere between 2.821 and 3.250. So I'll jot those down. 2.821 and 3.250. So I just put those on either side. And now, from there, I can scroll down, so here. So now I roll down here, and I want a one-sided p-value, so I'm somewhere between 0.005 and 0.01. Remembering the only kind of switcheroo they have to make is read the p-values from right to left, right? Because as we're going further and further out into the tail, right, the area in the tail is getting smaller and smaller, right? So 0.005 and 0.01. .005, 0.01. So now we know that our one-sided p-value is somewhere in there. Any questions so far? Is it okay? So F is, of course, our conclusion. Right, I'm just kind of walking you through it. So what can you conclude? Is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? So we use the same standard blurb, right? We have to compare the p-value to the alpha level. Here, we're not given an alpha level, so we're going to use 0.05, right? That's the default. So first things first, since our one-sided p-value is between 0.005 and 0.01, it is less than, both of those values are less than 0.05. It is less than our assumed alpha level of 0.05, which means if the p is low, then the null hypothesis must go, right? And so here we're saying our p is low, right? It's less than 0.05. So, which means we have enough evidence to reject H naught. If you're rejecting it, maybe say in favor of what? You could just end it there, that's fine. But in favor of HA. In terms of the question then, is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? We just reword that as an answer. Therefore, there is evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage. Any questions about that one? So that's a hypothesis test for matched pairs. And if there are no questions, we'll keep going to confidence intervals. We've seen this confidence interval before, so I'm not going to walk you through example 7. We'll just do example 8 together, because example 7 is typed up. So, but we can just talk about it. We've seen this formula before, right? The only new thing is that we have the subscript D or the subscript diff. Doesn't matter. Right? We have our sample mean that we're building our interval around, right? Our sample mean is our best guess at what the population mean might be, right? Plus minus, and then our margin of error is our T star, which we find the same way as for one sample mean, right? You find your degrees of freedom, which is the number of differences minus 1, and then find your confidence level, and that's how you find your T star, and then the standard deviation of the differences over the square root of the sample size of the differences, right? So I've got example 7 on here, but in the interest of time, we're just going to skip to example 8. But definitely look that over. So, example 8, A study tested whether wearing wetsuits influences swimming velocity. 12 competitive swimmers and triathletes swam 1,500 meters at maximum speed twice each, once wearing a wetsuit and once wearing a regular bathing suit. The order of the trials were randomized, right? So they're not all just swimming with the wetsuit on first and then going in their bathing suits again when they're all tired, but it was all randomized. Each time, the maximum velocity in meters per second of the swimmer, among other quantities, of course, was recorded. The summary of the data collected is found here. So, one kind of telltale sign if you're trying to figure out what type of question you have, right? For matched pairs, I have to give you the mean and the standard deviation of the differences, right? So sometimes it'll be a table like this, or sometimes it'll just be a blurb in the, I think was example, yeah, so example 7, it was just inside the blurb, right? So get used to reading both types, right? But definitely when you see something like this, sample 1, sample 2, and the differences, that's going to be a matched pairs for sure. Right? So there are these kind of telltale signs. And then just convince yourself that, okay, did we make 2 measurements on the same subject? Right? In this case, we did, right? Wetsuit, no wetsuit. When I was making this table, I was typing it up, and for some reason, I initially typed no swimsuit, something different. No wetsuit was the question. So we're going to compute a 95% confidence interval for the difference in average maximum velocity for the competitive swimmers and triathletes wearing wetsuits minus those not wearing wetsuits, blah, 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 right? But we have to make a confidence interval. One thing that someone in the other class asked, if I'm asking for a confidence interval, will I always say make a confidence interval? Yes, I will, right? So there's no other way for me to ask it without saying, construct a blank % confidence interval, right? Or use a blank % confidence interval. So it'll always tell you to make a confidence interval. All right. We have the mean and the standard deviation of the wetsuit, the no wetsuit, but also the differences, right? So if we've decided that this is a matched pairs problem, we can just ignore the wetsuit and the no wetsuit information, right? We could analyze those separately, but for a proper analysis, we analyze the differences. So for matched pairs, we analyze the differences. I'll just start writing out the type, right? Just to convince her, and it doesn't have to be anything extravagant, right? We're saying that this is paired data. Remember, I use matched pairs and paired data interchangeably, whatever comes to mind. So paired data, since each swimmer did the tests twice. So if we're making a confidence interval, right, first I'm going to write out, you don't have to, I just like to write out the formula that I'm about to use, just so I can check off and see what's missing, what information I have, right, and then I can plug in the values. But really what we're going to end up doing is we have to find T star, right, but X bar D plus minus T star times SD over the square root of ND, where X bar of the differences we said was 0.078 from the table. S of the differences is 0.022 from the table again. And ND is 12, because we have 12 swimmers doing the test. So we need T star, oops. My iPad's all jumpy today. Need T star for a 95% confidence level. Oops. With degrees of freedom equal to ND minus 1, which is 12 minus 1, which is 11. Because I've got all that information down, I can just look up T star on the table. So 95% confidence level and 11 degrees of freedom. So here, I get 2.201, unless looking at it wrong. 2.201. So T star is 2.201. Oh, critical value? Or, oh, need. Here, this one that I just erased. Yeah. And so now we have all the parts of our confidence interval. So now we can just plug them in. I'm going to start by writing out my formula again. X bar of the differences plus minus T star times S of the differences over the square root, the number of differences. You have to have those D's on there just to show me that you know that you're analyzing the differences. So we said, okay, we have 0.078 plus minus 2.201 times S, which was 0.022 over the square root of 12. .022 divided by the square root of 12 plus minus times 2.201. I get a margin of error of 0.013978227. Let me know if you get something different though. I'm going to store that, right, because I want to keep as many decimal places as I can until the very end. So if you don't know how to store stuff on your calculator, definitely come ask me about it after class. I'm sure it has some sort of storage function. So then our interval, right, we write it in round brackets, lower separated by a comma and then upper. So 0.078 minus the margin of error makes 0.064021773 up to 0.078 plus the margin of error. I get 0.091978227. So I gave you things to 3 decimal places. So you just match that if you're not sure. So rounding this to 3 decimal places, 0.064 up to 0.0. 0.09, oops, 2. It's already 3 decimal places. So, to interpret the confidence interval, right, we just have to keep in mind that we're analyzing the differences, right? So looking here, the difference is if these two groups were the same, 0 would be in there, right? But now we're going from 0.06 to 0.09. Both of those are above 0. So if we had to use this interval to say, well, is the mean difference 0 or not? No, here we would guess probably not, just because it's consistently above 0, right? So we have to think about the differences a little bit different than just one sample. But we just interpret it. And so we are 95% confident the interval from 0.064 to 0.092. And this is where you just reword the question as an answer. I'm going to shorten it a little bit just to save us some writing. Captures the difference in average maximum velocity. And I'll just end it there. I'll throw in mean difference here. I should have had that in the question. The mean difference in average maximum velocity. Okay, of the swimmers. Oops, swimmers. I'll just do a little side note here. Note, since this interval is consistently above 0, we can conclude there is a difference in maximum velocity. Any questions about that one? Okay. So, the last type of question that we're going to cover in chapter 5 is just 2 independent sample means that you want to compare, right? This is probably the most common one that we're going to do, right? So just in real life, right, you've got group 1, group 2, they're not paired in any way. You've just got these 2 means that you want to just compare. Right? And so then we have 2 independent sample means. And of course, we use the t-distribution still. Okay? So the only tricky part is that, okay, so now you've got group 1 and group 2, right? So, I don't know, typically with Okanagan College, UBCO, some numbers like that, right? So average tuition, let's look at that, right? So the mean tuition at UBCO versus Okanagan College, and now you've got these 2 independent means that you want to compare, right? And so the tricky part is that now there's no way around having these two columns, these two separate columns of data in your data set, right? There's no way to simplify them into the differences, because there's no way to say that, okay, well, this observation here matches this observation here, right? And so we've got these two groups. What's really kind of neat is that we could actually have different sample sizes, and we can deal with that as well, right? So if you're comparing males and females, for example, you don't have to have the same sample size. Often we do just for simplicity's sake, right? But you could collect 15 males and 19 females, and you could still compare those means with this t-test that I'm about to show you. But of course, each of these groups now, right, these are two independent groups, and so each group is going to have a sample size, it's going to have a mean, and it's going to have a standard deviation, right? So there's more information, or twice as much information, that we have to deal with than what we're used to. So just a little note is that the wording of these, so matched pairs or paired data, is when we're analyzing the mean difference, right? The mean of the differences. Here, if we're comparing two sample means, what we're doing is we're still going to subtract one mean from the other, but we've already found those means, right? So we're not subtracting the observations and then finding the mean, right? We're taking the means and looking at the difference between these two means. And so here we're analyzing the difference in the means, which is completely different. It sounds the same, but it's completely different. So again, I'm just going to run you through the general layout of the hypothesis test, but by now we're pretty familiar with the 4 steps of hypothesis testing. And so now all we really need to know is, okay, well, what does the null hypothesis look like? What does the test look like? And then you've got it from there, right? Because then you have a t, and you can calculate your p-value, and then you can draw your conclusion, right? And so, like I said, for 2 independent samples, your null hypothesis, just like in matched pairs, it's already predetermined, right? Your null hypothesis is going to be that mu1 is equal to mu2. You have to assume that these 2 groups are the same until you have proof otherwise. And so even if you suspect that they're not the same, you have to assume that they are until you have proof otherwise. Another way that you could write this is, okay, well, if they're the same, then you could say mu1 minus mu2 equals 0. I have this one on your formula sheet just because I think it's more concise, but if you prefer to use this one, that's fine. I'll highlight this. So we use subscripts for group 1 and group 2, right, to differentiate which group is which. And on the test, so for full marks on a test, you must use question-specific subscripts. Okay. For example, if you're comparing a group of males and females, you have to have mu m equals mu f, because that's how I'm going to know, well, how should they compare, right? Did you set up your null hypothesis correctly, right? So you have to have question-specific subscripts, and sometimes it's nice. Sometimes the question-specific subscripts are 1 and 2, right? That's fine, but just keep that in mind if you're comparing males and females, for example, or we'll see some other examples later on. Tricky part, right? Because we said, okay, we have all this sample information from 2 groups now, right? So we've got x1 bar and x2 bar. We've got s1 and s2, and we've got n1 and n2, because remember, they don't have to be the same, right? And so our t calculation is quite a bit bigger, right? We can boil it down a little bit, right? Because again, we always assume the null hypothesis is true. And so up here, right, where you had mu1 minus mu2, if the null hypothesis is true, that mu1 equals mu2, this will always be 0. So it's the same kind of situation as the matched pairs, where we said, okay, well, because our null hypothesis is fixed, this will always be 0. So what we're going to write instead, just to simplify things, is just x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. Don't forget those squares. They're only squaring the standard deviations. And then divide by the n. So, and we'll do examples, of course, just like before. But once you have your t, then it's easy street, right? Oh, I've got the actual, so your degrees of freedom, technically, you should be calculating this nasty bit here. Or we'll do this calculation. So, but for us, when we're doing these by hand, truly by hand, like we are, all we do is we say, we're going to take the smallest sample size minus 1. Right? And how we communicate that is we want the minimum of n1 minus 1 and n2 minus 1. Because the minimum function just says, return the one that's the smallest out of these two. And so if you're doing these by hand, you're checking your work in R, or just kind of working along in the lab maybe, then this is the degrees of freedom it will give you. But this is not what I want to see, right? And on your formula sheet, I just have this one, the smallest of n1 minus 1 and n2 minus 1. This is just your smallest sample size minus 1. And then once you have your degrees of freedom, you can use your t to find your p-value, and then you can draw your conclusion the exact same way that we have been doing. Right? So notice how only the null hypothesis and the test is changing, right? Maybe a little bit how we find our degrees of freedom, but not really, right? And then everything else is staying the same. Okay? So we've got this example, kind of a long one. I think this one's typed up or I know it is. So we'll just kind of read through it briefly, and then we'll do example 10 together. So weights of diamonds are measured in carats, and the difference between the size of a 0.99 carat diamond and a 1 carat diamond, you can't actually see the difference, right? And so if you're in the store and you're looking at a 0.99 carat diamond and a 1 carat diamond, they will look the same. Okay? The thing is that they're going to have different prices, right? And so what this question did is it just said, okay, well, let's compare if we translate 1 carat to 100 points and 0.99 carats to 99 points, then we can compare the point value of each of these diamonds, right? And so now we have a sample of 1 carat diamonds and a sample of 0.99 carat diamonds, right? There's no way to naturally say, okay, I'm going to compare this 1 carat diamond to this 0.99 carat diamond because they're independent samples, right? And so now we can calculate the mean and the standard deviation and the sample size of each of the two groups. Right? Notice we have different sample sizes, but that's okay. Is there evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds? Just looking at this, right? $53 versus $44. 53 is higher than 44. We just want to know if it's significantly higher than 44. We've got these all. So here, I've just defined, let group 1 be the 1 carat diamonds and let group 2 be the 0.99 carat diamonds. And then I've only used the question-specific subscripts in the null and alternative hypotheses. And then here in my calculation, you can just use 1 and 2 because sometimes the subscripts get a little messy. As long as you've told me what you're using as group 1 and group 2, that's fine. We first have to assume that the average point price is the same for the two groups. we suspect that maybe the average point price for 1 carat diamonds is higher than 0.99 carat diamonds. And so we have a one-sided test, right? Just because we've got this inequality here. Oops. One-sided test. We do the test. We calculate our t. Calculating our t is going to be a little bit more work, right? I want you to go through on your own later and just make sure that you get the same t, right? Keeping all your decimal places and such, right? Because you're going to want to keep in mind that you're squaring the standard deviation and then dividing by n and then adding them up. A little bit of BEDMAS in there. But we find a t of 2.507. Already, right, this is big enough for us to think, okay, there probably is some difference in the point prices, right? So we have to use our p-value to figure that out. And so here, using the t-table with degrees of freedom is the minimum of n1 minus 1 and n2 minus 1 is the minimum of 29 or 22. The answer is 22, right? So that's how this minimum function works. We find that 2.507 is between 2.183 and 2.508. And so our one-sided p-value is somewhere between 0.01 and 0.02. So then our conclusion, since our one-sided p-value is between 0.01 and 0.02, it's less than our assumed alpha level of 0.05. I didn't give you an alpha level, so we have to assume, and we use 0.05, which means we have enough evidence to reject H0 in favor of H8. This means there is evidence that the average point price of 1 carat diamonds is higher, right, significantly higher than the average point price of 0.99 carat diamonds. What you do with that information, I don't know. Probably just buy a 0.99 carat diamond. I don't know. But interesting nonetheless. Any questions about that one before we do one together? Okay. So example 10 then. A study examined the impact of the color red on how attractive men perceive women to be. In the study, men were randomly divided into 2 groups and were asked to rate the attractiveness of women on a scale of 1, not at all attractive, to 9, extremely attractive. It's not really what you think though. One group of men were shown pictures of women on a white background, and the other group were shown the same pictures of women on a red background. The results are recorded below. So we've got 2 groups. Right? These, the group of men, how many men were randomly divided? Looks like 15 plus 12 men were randomly assigned to the white background or the red background, and then they were rating the attractiveness. And so they found a mean of 7.2 versus 6.1 and a standard deviation of 0.6 versus 0.4. And so just as far as checking assumptions goes, the data for both groups are reasonably symmetric with no outliers. Good. Just because we have these smaller sample sizes. Is there evidence that the men who saw women on the red background rated them as more attractive? Looks like 7.2 is higher than 6.1, but is it significantly higher, taking into account the standard deviation, so the spread of each of the groups? So here, let's talk about the type first. This is 2 independent samples. Usually I can just, all I can think of is because they're just independent groups, right? So This one is probably, I'd say, the absolute easiest to pick out because there's no mention of the mean of the differences or the standard deviation of the differences. That would make it matched pairs, right? But here it's just two independent groups, right? So kind of self-explanatory that way. Two independent samples, since the groups are not or are independent. Not that helpful, but it's just that obvious. And remember I posted the assignment 5 practice, so extra practice. It's just a list of practice problems and you just identify the type. I posted the solutions, right? Because that way you can read through these questions and just figure out, okay, am I on the right track identifying these types? And you can go from there. So I'm going to start by saying let group 1 be the red group and group 2 be the white group. In my null and alternative hypothesis, just to make things clear, I'm still going to use R and W, but then in my calculation, right, because my formula on my formula sheet just has 1s and 2s, as long as I've defined them there and I'm consistent, you can just use the 1s and 2s because it makes it easier. Or if you want to use R and W, that's fine too. So step 1, I need all this room here. Step 1 is to state our hypotheses. H naught is that mu R is equal to mu W. We want to know, is there evidence that men who saw women on the red background, so is mu R rated them more as more attractive, so is mu R greater than mu W? Making this a one-sided test. Step 2, I'll move down here, oops. Do the test. And here's where I'm just gonna copy from the formula sheet, right? T is x1 bar minus x2 bar, oops, over the square root of S1 squared over N1 plus S2 squared over N2. If you look ahead a little bit on the formula sheet or even in the notes, you'll see that that huge square root is also in the confidence interval, just like it has been, right? We've been using the same thing in the denominator of the t as we have in the margin of error, right? And so what's nice about, if you've done this calculation once, finding the t, right, and shown all your work, right, then when you go to do your confidence interval, you can just say, well, from the hypothesis test, I know that this whole chunk is this value, right? So that's what's nice, is that you can save a little bit of time as long as you do it, show all your work once, you can recycle it for your confidence interval. So we have group 1, the mean of group 1 was 7.2 minus the mean of group 2 was 6.1 over the square root of 0.6 squared over 15 plus 0.4 squared over 12. (7.2 minus 6.1, we can start there. 1.1 over the square root of 0.6 squared is 0.36 over 15 plus 0.4 squared, 0.16 over 12. 0.36 over 15 makes 0.024 plus 0.16 over 12, 0.0133 repeating, plus 0.024, 1.1 over the square root. Don't forget that square root last minute. Happens a lot. 0.03733 repeating, square root that. 1.1 over 0.193218357. 1.1 divided by that guy. You getting 29 point something? You guys do it? I'll write it down, but it seems huge. 29.46428571. That sounds more reasonable. Did you get the same 0.1932? Yeah? Yeah. See, I don't know what's going on. Well, I do know actually this calculator is glitchy. 5.693040.853. As we learned on assignment 4, right, a t of 29 point whatever is possible, right? It just means you're definitely going to reject the null hypothesis, right? So it can happen. I just don't see a textbook question coming out with that huge of a number. So 5.69, still, we're definitely going to reject the null hypothesis, right? But let's do step 3. Oh, I guess this is approximately 5.693 to 3 decimal places. Step 3, we have to find the p-value. We use the same blurb using the t-table. With degrees of freedom equal to the minimum of n1 minus 1 and n2 minus 1 is the minimum of, I guess, 15 minus 1 or 12 minus 1, which is the minimum. You can skip that one if you want. Minimum of 14 or 11, which is 11. We find I'm going to stick the absolute value of t equal to 5.693. It's between 2 values. So, and we have a one-sided test. So our one-sided p-value is between 2 values. So now we can take our absolute value. Our t to the t-table with 11 degrees of freedom. And we go here, so 11 degrees of freedom, 5 point whatever, and we move out and we max out at 4.437. That's okay, we can write that down, right? We know that 5.693 is larger than 4 point, what was it? 4 point, I lost it. 437, thank you. Off the table, all we know is that it's less than infinity, right? And that's doesn't really matter, but if you want to fill that spot, you can fill it with infinity. Or if you wanted to, you could just not have this chunk on here, right? But because I like to start with the same setup all the time, right? For me, it's easier to look at this and say, okay, well, all I know is that it's less than infinity. I'll clean that up. If we go down to find our one-sided p-value then, all we can really say is that, okay, so our one-sided p-value for 11 degrees of freedom, 4.437, is 0.0005. Right, so 3 zeros, 5. So all we know is that we're even further out in the tail than that. So we just know our one-sided p-value is less than this. And so on this side, our one-sided p-value is less than 0.0005. The area in the tail at infinity would be 0. Right? If you've reached the end, then there's nothing in the tail beyond that. Right? So your one-sided p-value is technically between 0 and 0.00005. This here and this here is optional. If you don't want to write those, that's fine. I write those because I like to be consistent. So all we know, same as before, right, when we were off the Z table and we found the area in the tail is less than 0.00002. Maybe one too many zeros in there. No worries. We just know our one-sided p-value is less than this really small number. So it's definitely going to be less than any alpha level that we throw its way. And again, we don't have one, and so we use 0.05. So step 4 is our conclusion. Since our one-sided p-value is less than 0.0005, it is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught in favor of HA. Therefore, there is evidence, just rewording the question as an answer, therefore there is evidence that the women or the men who saw women on the red background rated them as more attractive. Neat. What I'm gonna do is, instead of finding new numbers, let's just do a confidence interval for this question, and then I'll post the notes for example 12 after class, just so you have the solutions for example 12. But it'll be the same thing, right? So a confidence interval, by now you're well versed, right? So I give you the confidence interval. It's a little bit bulkier, right? Because we've got information from the two groups still, right? But if we were to construct a 98% confidence interval, or the difference in mean ratings, I'll just end it there. So our confidence interval, right, x1 bar minus x2 bar, I'll put brackets around it just to show that that's going to be one number, right? The mean, the difference in the means is best estimated by the difference in the sample means, right? x1 bar minus x2 bar, plus minus t star times the square root of s1 squared over n1 plus s2 squared over n2. Here's what's nice when they follow the question, right? So part A, part B, do a hypothesis test, do a confidence interval, is what you can say is that, well, this whole square root is equal to, and you can just steal it from, as long as you showed all your work before, right? That's 0.193218357. 0.19832, I lost it. No, 0.19321. Does anyone else have it? I don't want to scroll again. 0.19321. 8357. Okay. From hypothesis test. So you can do that as long as you've shown your work once. Even if it turns out that it was wrong, I'll still follow through as long as you're consistent. That's fine. And I mean, if your calculation was wrong, not if it was all wrong. And then we've already done x1 bar minus x2 bar, which is 1.1 from the hypothesis test. Oops. Using the t-table, right? Because now the only thing that we need is the t star. So using the t-table with degrees of freedom equal to, and again, I can just jump right to it, right? Because this is from the hypothesis test. So you've already shown all this work, and you're welcome to recycle it as long as you do it cleanly the first time. So using the t-table with 11 degrees of freedom and a confidence level of, what was it, 98%, we find T star is, so we have 11 degrees of freedom, and we want a 98% confidence interval, and so here we are at 2.718. 2.718. So now I'll write it out again just because I can. X2 bar plus minus T star times the square root of S1 squared over N1 plus S2 squared over N2. We get 1 plus 1, or 1.1 plus minus T star, which is 2.718, times the, oops, and I'm just going to sneak in that value that we stole, 0.193218357. Right. And if you wanted to, right, you could just start the question here. I just wanted to show you, right, highlight where everything came from, and then you can just do that down here, just highlight, oh, I know this value is this from the hypothesis test, I know this value is this from the hypothesis test, right, and then you can just plug in the values. So now, our margin of error is 2.718 times 0.193218357. We get plus minus 0.525167494. Our interval, 1.1 minus that is 0.57483256. 1.1 plus that, 1.625167494. So I only gave it to one decimal place, but just to 2 decimal places, let's say 0.57 to 1.63. Oh, is it? I think they're both positive, right?
Well, 1, if you just like round it, 1 minus 0.5.
No, it's positive, yeah. 1 minus 0.5, yeah. But I'm like, let me think about it. No, yeah, so they're both positive, which if we think about our hypothesis test, and that's a good way to check in, right, is, okay, we rejected the null hypothesis, and so we're actually expecting both of these values to be above 0, just because, or both of them below 0, but because we decided that one was higher than the other, right, we're expecting them to be above 0. But that's a good check-in point, right, is, does my conclusion match what I'm doing in the hypothesis test? Good. So, so it makes sense that both of them are above 0. So we are 98% confident the interval from 0.57 to 1.63 captures, and what did I ask you? The difference in mean ratings Notice the difference between hypothesis testing and confidence intervals. So hypothesis testing, we're saying, okay, yes, there is a difference. Confidence intervals, let us say, okay, well, here's where we're pretty sure the amount of the difference is, right, between 0.57 and 1.63. Okay. So that's all of chapter 5. Like I said, I'll post the solutions to example 12, but other than that, you have everything. Grab the practice test if you didn't grab one already, and show me some of that work on Wednesday. See you then.